Very good morning to all of you from France. I'm Christophe Cazaban, and I'm going to talk to you today about the field application of the SIR model for the control of disease transmission. Just to get started, let's trace together that today's poultry industry is definitely a wonderful success story or a model for production efficiency. In a few words, we started less than a century ago with a family-based small business into a very large production complexes that we can see today all around the world, where we can see dozens and dozens of houses that are going to keep millions and millions of birds together in the same place. So all of these towards a better yield of production for an always affordable price to feed a growing world population. So that's extremely efficient, that's extremely successful. On top of that, we also know that the geographic repetition of these poultry industry is not even. When we look at some of the recent USDA mapping, we can clearly notice some areas where you are getting a much darker spots or a congregation of spots, just highlighting that indeed in some areas we are dealing with a very high density of broiler farms, of broiler complexes belonging to different companies. And probably one of the best examples is the Delmarva Peninsula, where we can see from this schematic that in a very short area, you see the scale here on the top right, we do observe a huge amount of poultry houses that are definitely belonging to different companies. So it's extremely high density of poultry production. So the question here is that, is there any Achilles heel into this business model? And I would say that, yes, indeed, the today's poultry industry is definitely a model for production efficiency, but we have to keep in mind that the spread of viruses and the uncontrolled spread of viruses still represents a quite significant Achilles heel of this production system. One of the widely described example is the LT spread out that was described, for instance, a few years ago, where it was very, very clear, according to this map, that we could easily trace back the occurrence of these LT cases. And obviously, when you have such a close-by industry next to each other, then a contagious agent can jump very, very easily from one complex to another, or from one barn to another. So let's take the example today of the lontogenic paramyxovirus type 1, like vaccine strains of Newcastle disease, or sometimes exotic Newcastle disease. That's what's gonna happen in this type of high density area. So let's have a focus on, let's say, one of these complexes, and let's imagine that by chance, through a breach in biosecurity, one of these house is getting hit by Newcastle disease virus, either exotic Newcastle disease or lontogenic PMV1. In case of improper immunization or immunity into these houses, then the virus is likely to get propagated and to spread from house to house, and getting even in a larger amount spreading to the other neighboring house. And ultimately, this will result into a massive spread and contamination of the environment, as you can see, using a huge, much larger amount of virus compared to the initial one. So you can imagine the consequences of such an outbreak in an extremely dense populated area like the Delmarva Peninsula. Not only direct production losses for the company that has been hit for the very first time, like poor flock uniformity, higher condemnations at processing plants, but obviously there can be a massive spread towards horizontal spread towards neighboring operations, companies, and even counties. That makes it completely out of control. Okay, so What can be done in this scenario? Let's have a look at the lessons that we learned from the recent COVID-19 pandemic. I'm going to discuss today about the transmission and the pattern of transmission. We know perfectly that if, like in this drawing, one infected person spreads the virus towards 2 other people, and further on, these 2 other people are spreading it to 2 more people, then it's getting exponentially spread out to a massive amount of population. So what if we could find a way, like social distance, for instance, like facial masks and so on? What if we could find a way to reduce the likelihood of transmission among human beings? Definitely, as we can see from this obvious drawing, then the extent of transmission will be dramatically reduced. And this is where this SIR model comes into place. Actually, that's an acronym which stands for susceptible, infectious, or recovered. This is so-called a stochastic model. Stochastic basically means statistics applied to probability. So now let's have a look at how we can apply it practically in the poultry industry. We can also identify either susceptible birds or infectious or recovered ones. Unfortunately, we have also to consider that likelihood of some dead birds. The ideal vaccination should aim at reducing the susceptibility, reducing the likelihood of a bird becoming infectious, and obviously reducing the mortality rate and reducing the clinical symptoms in general. But this is very much considering the individual level. Now, let's look at the flock level. And this is where I'm going to introduce the so-called reproduction ratio, R, that I'm going to describe later on. If this reproduction ratio is equal to 2, then one bird will be able to infect 2 birds, and each of these 2 birds will be able to infect 2 more birds. So can we imagine a vaccine that would bring this R value down to 1, simply meaning that one bird will be only able to infect 1 more bird and 1 more bird and so on? And what if, let's dream, if a vaccine would be able to completely stop this transmission? Is it doable? Is it something achievable? I'm going to share with you briefly the data that are accessible through this recent publication that our teams have issued together with experts in statistics from Utrecht University in the Netherlands. We used as a model vaccine Vectormune ND, but of course, as you know, it was used as a backbone to build up Ultifen's IBD ND, which is, according to the construct, exactly similar to Vectormune ND, just including VP2 insert from IBD on top of that. So I believe that what is demonstrated for Vectormune ND is certainly also usable or valid for Ultifen's IBD ND. So the aim of our study was to quantify the transmission likelihood and speed and extent of a velogenic Newcastle disease virus among vaccinated broiler chickens. To do so, we had to calculate this reproduction ratio, R, which basically means what's the average number of secondary infections that are caused by one single infected bird. And to do so, we have to apply a formula which includes 2 figures. One is called beta. This is the transmission coefficient. So basically, how many infections do we experience per infectious bird and per day? And this beta parameter has to be multiplied by T inf, which stands for infectious period. So very simply, for how long this infectious bird is actually infectious. So very briefly, we use commercial broilers and we allocate them randomly per group. So we had one first group, which was the vaccinated group that received Vectormune ND, full dose at day old. And these vaccinated birds were later on split into two groups at 42 days of age. Half of them were getting directly inoculated with the velogenic strain of Newcastle disease virus, whereas the other ones were not inoculated, but they were brought back 8 hours later in contact to these directly inoculated birds. In the same way, we kept control birds, obviously non-vaccinated, and as you see, at 42 days of age, approximately half of them were also either directly inoculated with the velogenic virus or kept as a contact that were brought together 8 hours later. So just to represent in a schematic form, the vaccinated birds, half of them were directly inoculated with the velogenic Newcastle disease virus at 42 days of age, and 8 hours later, they were brought into contact with these contact birds. And the same was done in the control birds that were not vaccinated, but half of them were directly inoculated, and they were acting as the seeders brought into contact with contact birds 8 hours later. So we try to answer the following questions. First of all, to what extent did the vaccine increase the resistance to the infection at the individual level? To what extent did the vaccine reduce the immediate shedding, namely the extent and the duration of the horizontal spread, so which is the basic parameters that are done or that are monitored in any type of experiment. But on top of that, because of these later contact birds, we also aimed at assessing to what extent did the vaccine increase the resistance to the horizontal spread to these contact birds. So to do so, what we run is that we run some daily swabbing samples from oronasal cavity as well as from the cloaca, and this is also quite unique because, as you know, most likely in some challenge experiments we are collecting some swabs, but especially during the acute phase post-challenge, so which includes a couple of days. But in this particular experiment, we did it daily for 14 days after challenge. And we've run a specific, obviously, real-time PCR to look for the challenge virus. And then the Dutch statisticians applied their SIR model using this mentioned here formula and statistical models in order to come up to this R value. So what are the results? Very quickly, as expected in terms of survival, the control birds, they died very quickly. That's the directly inoculated ones here in red, and the orange ones are the contacts that are dying after a few days. And the vaccinated birds, you see here the green diamonds and the blue square, they were totally protected against mortality. So the challenge model was validated, of course. Now, when we go to the shedding of these directly inoculated birds, again, the results were somehow as expected. Namely, on the right-hand side, the control birds were very quickly shedding a large amount of virus from both oronasal and cloacal swabs until dying, whereas the vaccinated birds were shedding much less and for a much shorter time frame, mostly from oronasal cavity, and as you see from the cloacal swab, it's very, very minimal. And obviously, the different rates of shedding were statistically significant. But what's critical for the assessment of this transmission among birds is the pattern of shedding among the contact birds. They have not been directly inoculated, but just brought into contact with the directly inoculated ones. And here again, we do observe a very dramatic different scenario between either the unvaccinated ones that are shedding a very high amount of virus until dying, whereas the birds that were brought in contact with the vaccinated ones, they were shedding a very minimal amount of virus and for the very short period of time. So if we put that into figures to make it more tangible, we came to the following information. First of all, the vaccination enabled to significantly reduce the length of the infectious period. In practice, it went from 4.8 days down to 3.4 days, and this is significant. And obviously, in the unvaccinated ones, the outcome was the death, whereas in the vaccinated ones, the outcome was the survival. So this is first criterion, the infectious period. The second criterion, which is the transmission coefficient, you remember, is also dramatically reduced and significantly reduced from 0.67 in unvaccinated down to 0.24. This beta coefficient, transmission coefficient, basically means that the horizontal spreads of the infection among vaccinated broilers was almost 3 times, actually it was 2.8 times to be accurate, as slow as compared to the unvaccinated birds, which basically means that it gives more time to intervene. It gives more room, more air to the, biosecurity measures, the population, if needed. And then when we multiply these two numbers to end up into R, so reproduction ratio, we did observe that, yes, indeed, this particular vaccine was able to bring the reproduction ratio below a figure of 1. And this was, again, statistically significant compared to the 3.2, which is the reproduction ratio in the fully susceptible birds. So that's obviously extremely important. And when we go even further than that, meaning that we calculate or we assess, if you like, the likelihood that a virus introduction into a flock would result in an outbreak or not. So to do so, we have to calculate the following formula, 1 minus 1 divided by R. Since R in vaccinate is less than 1, then this likelihood becomes negative, which basically means that most virus introduction into a well-vaccinated flock would not result in an outbreak in such complexes, whereas they would result in an outbreak in 69% of the introduction in the unvaccinated or poorly vaccinated flocks. So what are the lessons learned from this experiment and this calculation is that by getting in the same time fewer outbreaks as well as smaller outbreaks, we get less between flocks as well as less between farm transmission possibility until the transmission will be completely stopped. So that's obviously extremely important. And why is it like that? What's the potential explanation for that? It's most probably due to the strength and breadth of immune stimulation that we are provided with Vectormune ND or with Ultifen IBD ND. We have already demonstrated that this type of vector vaccine is able to strongly stimulate in the same time humoral as well as mucosal and cellular immune pathways. So that's probably one explanation for this amazing result. So very practically, for free countries like the United States, this is very important because it means that such a vaccination approach could indeed help, because the aim of the policymakers, of all stakeholders, is basically the prevention of outbreaks or prevention of further spread of a disease, because we are in a non-endemic country. And this is doable. We have demonstrated that. On the other hand, in endemic countries where the challenge is much higher, remember that we are usually applying a couple of live vaccines on top of the vector vaccine. So we can even dream that there will be an even further improvement of the transmission reduction capacity. So just to represent this in a very simplistic way, if we are getting a full complex, very well vaccinated like this with Ultifant, and if by any reason one of these houses has for some reason medium or poor protection against a breach in biosecurity, and it has been hit by the virus, and the virus is spreading towards neighboring houses, then the further spread to the neighboring houses and to the neighboring complexes will be stopped, will be halted because of this strength of protection. So for the very first time, we were able to demonstrate that a very powerful vector vaccine was able to bring this reproduction ratio below 1, and in such a way it's able to induce less virus shedding and a very significant reduction of the likelihood of virus transmission among birds. So this should be regarded as a premium tool for outbreak control and prevention of ND or exotic ND, especially in non-endemic regions, besides biosecurity measures, of course. And I thank you very much for your attention.